Well, let's talk about an ideal gas law application. Unlike solids and liquids, the density of a gas changes with environmental conditions. And this makes sense when you think about the fact that gases do not have a defined volume. So under certain conditions, the volume will expand, and since the mass doesn't change, that will lower the density. But in other conditions, the volume will compress. And as that volume compresses, with the mass remaining the same, the density goes up. So we need a way to calculate what the density will be given a certain gas at certain environmental conditions. So first we're going to start with the two equations you know for density and the ideal gas law. PV equals nRT for the ideal gas law, and density equals mass over volume. And one thing you've likely learned in your math class is that if two equations have the same variable, you can actually combine them into one equation. We do this by setting both of these equations to volume and then combining them into one equation by eliminating that volume variable. So we can rearrange the PV equals nRT equation into volume is equal to nRT over P, and then we can also rearrange the density equation into volume equals mass divided by density. Now since they're both equal to volume, if nRT over P is equal to volume and M over D is equal to volume, well then that means that nRT over P is equal to M over D. And then to make this density equals something, we're just going to cross multiply pressure and density to the other side and then divide by nRT on both sides to get density by itself. This will give us that density is equal to the mass of the gas times pressure over moles of gas times R times the temperature in Kelvin. But how does this all equal density? Well, just let's look at the units real quick to prove it. It's a density because the density is equal to, well, mass is in the unit of grams, pressure is in the unit of atmosphere. We're going to have moles in the unit of mole. R is in the unit of atmosphere times liters over mole Kelvin. And then temperatures in the unit of Kelvin. And we're going to see that our Kelvin units cancel out, our atmospheres cancel out, our moles cancel out, and we're left just with grams per liter. Grams being a unit of mass, and liter being the unit of volume for a gas. And while this equation is very useful for finding the density of the gas, we're going to take it one step further, and we're actually going to incorporate the molar mass of a gas in this equation as well. Remember, the molar mass of any substance is equal to the mass of that substance in grams divided by the moles of that substance, grams per mole. And just like above, where we were able to substitute when the same term was in two different equations, we're going to do that here. So molar mass is equal to M over N. And our density equation also has that same M over N. So let's just get it by itself so we can substitute. We'll multiply both sides by RT over P. And in doing so, we'll get this equation where dRT over P is equal to M over N. And since molar mass is equal to M over N and dRT over P is equal to M over N, then that means molar mass is equal to dRT over P. And this is a super useful equation, but we don't want to derive it every time we need to use it. So it would be nice to memorize it. And Miss Weck has taught me a really easy, funny way to memorize it. What animal hides their pee under the dirt? DRT dirt, P pressure under the dirt. Well, a cat, of course. Meow, meow. The molar mass is equal to dRT over P. Give these problems a try using our equations from the previous page, and I'll be back in a moment to show you the solution. So in this first problem, we're told that we have 176.04 grams of an unknown gas that occupies 89.6 liters of volume at STP. And we want to know what is the identity of the unknown gas. We're told it could be CH4 methane, it could be oxygen, neon, or CO2. Well, ultimately, to find the identity of the unknown gas, we're going to use the molar mass equation. By solving for the molar mass, we'll know which of these gases it is. However, to use this equation, we need to know density, R, temperature, and pressure. Well, temperature and pressure are easy because we are at STP. So we know that the temperature is going to be 273 Kelvin and the pressure is going to be 1 atmosphere. R is also a constant, 0.08206, so we don't have to worry about that. So really, we just need to find the density. Well, density is just a mass over volume, and we're talking about gas density, so it's grams per liters. So we take our mass divided by our volume, and we find that our density is 1.965 grams per liter. Then we just plug our values into our equation, and we find that we're going to have our liters cancel out, our atmospheres cancel out, our Kelvin cancels out, and our answer will be in the unit of grams per mole, which is a molar mass. When we calculate our answer, we find that our molar mass is 44.0 grams per mole, which is CO2. In the next problem, we want to know the density of chlorine gas at STP. And while I've memorized the meow meow, pee under the dirt equation, we can rearrange this quickly to get into a density equation, where it's going to be density is equal to the molar mass times pressure over RT. But we just have to remember that chlorine is a diatomic element, so the chemical formula is Cl2, and that means the molar mass is 70.90 grams per mole. We then input our values into our equation, and since we're at STP, that means that our pressure is going to be 1 atmosphere and our temperature is going to be 273.15 Kelvin. If I look at my units, my Kelvin unit cancels out, my mole unit cancels out, my atmosphere unit cancels out, and I'm in the unit of grams per liter, which is a density. I solve my answer and I find that the density of chlorine gas at STP will be 3.16 grams per liter. And then in this final problem, we have 5 different gases, each of them at 25 degrees Celsius and at 1 atmosphere pressure. And we want to know which sample would have the lowest density. Well, again, density is molar mass times pressure over R times T. So if these are all going to be the same for each gas, really this is basically just comes down to which one has the lowest molar mass. Because if we look closely at the units that ultimately result in this answer, the grams part of the density unit comes from the molar mass, which makes sense, molar mass. So as you increase that mass, you're going to increase the density because the volume is not going to change from the other values. But as you decrease that molar mass, you're going to decrease the density, which means my answer is going to be ammonia because ammonia has a molar mass of approximately 17 grams per mole, where the next lowest thing is oxygen, then argon, then CO2, and then lastly nitrogen dioxide.